Well, friends, we have with us three distinguished dignitaries and eminent scientists who are here in Mangalore University participating in the second international conference on polonium and radioactive lead isotopes. We thought it is indeed a privilege on our part to invite the chief guest for a panel discussion. We have Professor Thomas M. Church, University of Delaware, New York, United States. And we have Professor Fernando P. Carvalho, Technical University of Lisbon, Lisbon, Portugal. And we have Professor Mark M. Bhaskaran, Wayne State University, United States. And I request Professor Bhaskaran to be the moderator.
We have a three-member panel, and let's start this with a brief introduction of the panel members. My name is Mark Bhaskaran, moderator of the panel. Next one, the one right to me is Professor Tom Church. Can you please introduce yourself?
Yes, I'm from the University of Delaware. It's School of Marine Science and Policy. I'm also in the chemistry department, which is my background. I work in transfer of materials from the land to the sea. In particular, I focus on inorganic elements, pollutants, and their fate during atmospheric transport and deposition, like rainfall to the ocean. And we use certain tracers that are the subject of this conference into tracing these materials as they enter the sea and onto their particles and organisms. Thank you.
The one next to me is Professor Fernando Carvalho. Can you please introduce yourself?
With pleasure. Thank you very much. I come from Portugal, where I am a researcher at the Nuclear Technological Institute, which is part of the Technical University of Lisbon. For the last 30 years, I've been working on environmental radioactivity issues, and this includes, for example, radionuclides that may be spread in the environment from uranium mining operations, from the releases from nuclear power plants, and from other many common activities that may enhance the radiation exposure of the population. We are interested in assessing the risks for the public health derived from these pollutants when they may eventually be dispersed in the environment.
There are more than 92 elements that commonly occur in nature. Of these 92, this workshop focuses on two elements, lead and polonium. The main purpose of this workshop is to understand how these two elements move, how much radiation they emit, how much it can cause problems to human health, and how these elements can be used to understand various processes on this earth. So towards that, I'm going to ask the panel members some questions. So first, I will turn to Dr. Carvalho, and I will ask a question. What is polonium and lead? Why do we have a conference on that?
Well, polonium and lead are two common elements that exist everywhere in our planet. They exist in the atmosphere, they exist in soils, they exist in the water, they exist in the plants and animals. There's something special about these two elements, like the polonium you mentioned, and some varieties of lead. They are radioactive. They emit radiation. And radiation is a subject very important for all living organisms, and in particular for man. It's not possible to deal with all the issues simultaneously, so this conference has selected these two elements to tackle, to bring together specialists in order to discuss results of recent research, in order to exchange ideas and try to understand better the behavior of these two radioactive elements and how they may affect the human beings. On the other hand, we know that we may use also these radioactive elements to investigate some natural processes in nature. As Thomas said, we may use them to understand cycling of substances in the ocean. And this is the purpose of the conference, is to bring together the data and the knowledge that we have about these two and to plan the work forward.
One term that you commonly come across is isotope. You can understand that term isotope as follows. Suppose you have two tennis balls, and the two tennis balls are very identical except the masses are slightly different. So like one element has many isotopes, they look more or less the same, but the weight of one is different than the other. Why we solely focus on polonium and lead? Dr. Church?
Well, fortunately, in this family of elements, one of them happens to be a gas. And it's what we call a noble gas, means it has no chemistry or reaction, and it's emitted from the surface of the Earth continually. It is also radioactive. It's been in the news because in certain confined areas, such as in uranium mines or in people's basements, levels of this gas can perhaps cause some concern. For this conference, though, we might call it the father of these other elements, produces these two, a daughter and a granddaughter. One of them is a lead isotope and one is the polonium isotope. And so they're related like a family is, in that one is born and then gives birth to the other one. And that happens at a very precise moment. And so we can use the two together, just like you could a mother and her daughter, to follow their progression through life, or in the case of these elements, into the environment, whether they're falling on the land and proceeding down the rivers, or they're falling into the ocean and proceeding to make their journey through the sea.
What we learn about these polonium and lead isotopes is to study various kinds of processes, and also they undergo radioactive decay and they produce radiation. So the radiation, we know it's bad. We will ask our expert panel member, Dr. Corvallo, why excess radiation is bad, how much radiation our body receives.
Well, that's a good question, because actually we often talk about radiation and radioactivity, and the first thing that we should know is that all of us are exposed to some dose of radiation, because our planet contains naturally occurring radioactive substances. Of course, this is known of the people in India, because Kerala is known because of some sands that are special in high thorium content. But we know that on one hand, these substances occur naturally in the environment, and we have been all life living together with them, but under certain circumstances, if they become too much concentrated, we may receive a too much high dose that could be detrimental for human health. For example, if we work in an uranium mine, the workers these days need to take special precautions, and the labor is organized in such a way to prevent the miners to be exposed for too long time in the mine, or to inhale the dust and the gas from the radioactive ore. In other circumstances, we may also have enhanced concentrations of these naturally occurring elements. For example, we may have accumulation of some type of wastes that may contain high concentrations of radioactive lead or high concentrations of radioactive polonium. So to avoid this, the consequences of this, we need to understand what is the action of these radioactive elements on humans, and what kind of preventive measures should be taken in order to avoid any undesirable effect on the public health. That is one of the reasons why we came and we are discussing in this conference.
why do we study these in the oceans, these lead and polonium? Extensive work around the world, researchers have studied. What do we get out of this, Dr. Church?
Well, lead is an element that likes rocks or pieces of rocks or particles, dust, for instance, and as soon as it is introduced into the ocean, either from the rainwater or from the great-grandfather, which is radium, immediately finds a piece of dust and stays with it. On the other hand, its daughter, polonium, likes organisms, and so it'll find and become associated with the algae or the fish that are in the ocean. And so these two, the mother and the daughter, become separated in the ocean, and both of them have in their radioactive properties a very fixed rate of decay or dying away. No matter what happens to them, that clock, so to speak, keeps on ticking. And so we have a clock that goes with the particles of minerals and dust that are settling in the ocean, and we have a clock that is in the organism that may be eaten by another organism and then finally deposited to the deep ocean. So these become like individual clocks that we can tell the rates in which processes occur. And this is important because in order to use the ocean for disposing of any materials, we'd like to know how fast they process and dispose of these materials. So that's their use in the
Thank
ocean.
you. What are the reasons you study lead and polonium?
The reason is that because of their radioactive properties, they're quite easy to detect. In other words, we put them in special instruments and wait for the radiation to emerge. And it turns out that this radiation is rather high energy. It's even higher energy than sunlight. And so we can detect these in very low amounts. And so by using other isotopes, we can do our chemistry rather simply and efficiently. The other reason that I like to do this is that in the case of lead, it also happens to be a toxic element. We had lead in our gasoline and took it out because it interferes with our neurological system, our thinking, and in the case of polonium, it's also a toxic element, and unfortunately has been used in some cases to poison people. So this doesn't happen, but it is because of the high energy, particularly for polonium, that we are concerned about its health. Also because it comes from other sources, such as when we burn our fuel for heating or electricity, the polonium tends to be vaporized and be volatile and then enter back and be transported with the winds and then concentrated in maybe things we eat and so forth. And Dr. Cavallo knows this very well.
In addition to these isotopes of lead and polonium, they travel around the Earth. They can get transported to several hundreds and thousands of kilometers from the place where it was released. Suppose if someone were to do some nuclear test and release large amount of radioactive material in the atmosphere, it can travel to several hundred or several thousand miles within a few days. For example, there was a major accident, as you all know, Fukushima in Japan. The nuclear material released from Fukushima went around the Earth and came back to Fukushima in less than 10 days. So these isotopes or these elements, how long it stays in the atmosphere, we can get those information using these isotopes. So these are used in the atmosphere, in the oceans, in lakes, in groundwater. Also, one important study is what kind of environmental changes are taking place. How much pollutants we are putting in our coastal waters, in our lakes, all those we can reconstruct. To reconstruct, we must have a tool of finding out the age. That's where lead-210 is used to determine the age of these sediments. Dr. Carvalho, I would like to ask, a common man gets worried about radioactivity in the environment as it can cause health-related effects. What would you tell to our audience?
Well, I think that, as I said before, we are all exposed to certain degree of radiation dose. It is not a matter of concern when it stays at the normal levels as we are used to. It could be a matter of concern when, for example, you mentioned the case of a nuclear power plant in Fukushima, Japan, that where something went wrong, an accident, a nuclear accident occurred, there has been a release of radioactivity. The amount of radioactivity was significant, and there has been an impact, especially in the region nearby, the local of that nuclear power plant. Some radioactivity was spread around and reached in the American continent, the European continent, the Asian continent. Many laboratories around the world were able to make the measurements to quantify the amount of radioactivity that reached every corner of the planet. And we know that in most of the continents, the amount of this artificial radioactivity released by the accident are of no concern from the public health point of view. So there will cause no visible harm, no measurable harm or detriment in the public health. On the other hand, if the amount of radioactivity released have been higher, or for those that unfortunately were exposed but they work at that workplace, the effects of a high exposure to radioactivity, of course, may, with time, may, for example, cause cancer disease. And this is one of the reasons why you need to know more about radionuclides, about radioactivity, about the special substances or elements. Some, like this polonium and lead, occur in the planet, naturally exist. Others are produced by man in the nuclear power plants, and we need to know much more about them in order to prevent the impact of these accidents on the environment and on human beings.
Thank you. Dr. Church, what would you say?
Well, what we often want to do is to have a way to what we call trace some of these pollutants. And so because these radioactive elements, and I will give the example of lead again, because they have the same chemical properties, we can trace, for instance, where all the lead comes from in smelting, for instance, or in the past, as we've added it into gasolines and it is now into the ocean. And so what we call the half-life, or the clock in lead-210, is 22 years. And so 22 years, which is about the time scale in which human beings live, is the rate in which we can trace the fate of lead material. You had mentioned using it also to date sediments, and this is exactly the type of rate that we would want to see for coastal or lake sediments that in recent industrial periods have been receiving the fallout or the introduction of toxic materials. And so we can say quite precisely when these materials were introduced, whether our efforts to control their emissions are being effective, in other words, are they decreasing, and also again to match the rate in which they were produced with the rate in which they're being disposed of in the sediments. It's kind of like keeping your bank account. You like to know how much is going in and at what rate, and how much is going out at which rate.
Thank you. Let's digress from our path and ask some questions on the potential risk of energy extraction from nuclear reactions. Occasionally we have had nuclear accidents, such as Green Island accident in US, Chernobyl accident in 86 in the former Soviet Union Republic, and more recently Fukushima in Japan. Can you share your insight on this issue as common person gets paranoid about radioactivity? So I will ask both panelists. Dr. Carvalho?
Well, yes. First of all, let me tell you that there is no industrial human activity without accidents. It's very common that when we try to solve problems of humanity, such as producing food, producing cars, producing energy, that's normal because we are not able to construct or to build the perfect machines. It occurs, unfortunately, always there is a chance to occur an accident. It occurs in spite of all the investment in knowledge and in money in the engineering of nuclear power plants. There has been a number of accidents that took place. The recent accidents, such as the ones you mentioned, that were, of course, worrisome for everybody, I think, from my point of view, I think they ring a bell. They call us the attention that we still need to put more efforts in constructing better and improving the safety of nuclear reactors, controlling better the nuclear reactions and all the systems that are in operation in a reactor to make it even safer than they are. I think that unfortunately these days there are no much room, no much option to just simply shut down the nuclear power plants because there is the risk of an accident, because we still need the large amounts of the energy that they produce, and if we are not ready to live without that energy, there is only a way to go, is either to find another alternative ways to produce the large amounts of energy we need, and meantime, if you have nuclear reactors in operation and if you need to continue for some time using nuclear power plants, then we need to invest more in safety, in engineering, and in the knowledge on how to protect us from radioactivity. So it brings us back again to our activity as scientists. We need to have better knowledge on all these radioactive elements, not only the ones that may come out from a damaged nuclear power plant, but also those that occur in the planet. We need to understand perfectly their chemistry, their cycling in the environment, how they pass from the water to the fish, from the fish to man, how they are ingested, how they are incorporated, what is the risk. And this is true not only for radioactive elements, but this is true also for many metals and many other substances that are part of our environment. We need to know more about our planet in order to manage and preserve it better.
Thank you. Dr. Church, your perspective on this?
Well, industrial society will always need energy, and some countries rely more on nuclear energy. I understand in India it's not very much, only maybe a few percent, and so no matter what we do, there'll be some nuclear energy, and as Dr. Carvalho said, we need to understand and engineer that type of energy better, because it has one very important facet, which is it has, if it's done correctly, has no emissions of harmful materials to the atmosphere, unlike what we call fossil fuels, coal, oil, gas, for instance. Now, the one property of polonium, for instance, it's like sulfur, and so when you burn coal, and this is one of the interesting things about a conference like this, is you learn new things. And just this morning, we had some presentations of the amount of polonium that is released during some of this power production, one on oil and one on coal. And it turns out that most of it is lost up the stack. It's not efficiently removed along with fly ash. Now, polonium only has a 3-month half-life, 138 days, but still, because, as you said, these are efficient transport processes, and they tend to get, into maybe substances that we consume, there is some concern. I also will give you one example. It's tobacco. Now, tobacco tends to love polonium. It eats a lot of polonium, And so for those who smoke, you're also smoking polonium. Now, there has never been any direct medical evidence, but there's suggestions. So this is, again, an example that maybe where there's some future research. Because once again, we're talking about an element that has extremely high radiation properties, and you don't want them inside your body, because that's where they can do some real damage.
Thank you. Let's summarize this particular aspect, that nuclear energy is the cleanest energy possible. It's cheap, easy to produce. The only thing we need to worry about is the safety and also securing the nuclear waste generated. All the other fossil fuels release carbon dioxide. For example, 1 liter of petrol releases 3 kilograms of carbon dioxide to the atmosphere. So, is there a consensus that nuclear energy is the safest and cleanest energy?
Well, are you asking my view on that?
Yeah, right.
Well, there is no broad consensus on that, but even the, let's say, the ecologist groups, the green groups in Europe, I may recall that, for instance, there is a strong party, Green Party in Germany, with an expressive presence in the parliament, that for maybe 10, 15 years as opposed to nuclear energy. But in recent years, faced with evidence that burning coal, burning fuel, releases even more radioactivity into the atmosphere, and I may also add that the combustion of plant biomass also releases significant amounts of radioactivity into the atmosphere. In comparison, it turns out that a nuclear power plant that is in perfect functioning, that is without any record of accidents, is cleaner than a coal-driven power plant. So if we take this, of course, we easily came out with the conclusion that it's a cleaner energy because it doesn't contribute to the greenhouse effect like the coal and gas. Of course, we still have concerns that relate to the waste of nuclear power plants. The radioactive waste of nuclear power plants do not have yet a satisfactory solution. So in order to make it an option, a long-lasting option as energy source, we need to find a suitable confinement procedure able to contain radioactivity in the used or spent nuclear fuel.
Okay.
In this respect, I would say that we do not have all answers yet, and probably other options will come out from the laboratories, and will provide in the future a contribution to solve our huge needs for energy in human societies. I'm thinking about fusion, but also in energy from windmills, energy from waves in the ocean, that eventually would be cleaner.
Yeah.
Right. It's only what we call renewable energy, whether it's from the sun or from the water, that is sustainable, because we will have limited resources, whether it's uranium for the nuclear power plants or the coal and fuel. And so we will never satisfy all our energy needs by wind and solar, but we need to start that process so that we have a downward use dependence on what we call non-renewable resources.
Good. Thank you. We will end this interview with this last two questions. You have 20 seconds response on your experience with this workshop organized at Mangalore University in India. Dr. Church?
I've been coming to India since 1980, so that's 25 years or more. And I'm well attracted to this country because I find it's, first of all, his people so magnanimous and friendly and tolerant. And it is the model, I think, of diversity. I come and I see dozens of different languages, coexisting several religions side by side. And I think the Western world can take some examples of this and how you can live in a burgeoning, wonderful, industrialized economy like India. And so I hope that I can continue to return.
Thanks. Dr. Karwal?
Well, I take the pleasure to say that I fully support your view. I share your view. I would add that from my personal perspective, that for me, as a Portuguese, was very attractive to come to India and to visit friends that have been friends for 5 centuries. For me, it has been a pleasure. It has been a pleasure to be here working during several days with professors and teachers and colleagues from all over the world, but also the ones from Mangalore University. And I must publicly express my acknowledgement for the wonderful welcome, the wonderful time, and the conditions also that the University of Mangalore and the city of Mangalore has provided to our work. I personally am very pleased, and I will return.
Thank you very much. Namaskar.